This video is going to recap and review regression, which is chapter 3, and then we're going to talk about a little bit about inference for regression. So this is good because it's going to help you to review for your AP, because we're going to review a topic that some of you told me that you don't remember. So remember, regression has to do with bivariate data. Bivariate data means two variables, and specifically they are quantitative, which means they are numeric. The explanatory variable is the x variable, and that's also known as the independent variable. And the response variable is the y variable. So remember, when we're making a scatter plot, the x variable goes on the x-axis, the explanatory. On the y is the response. That goes on the y-axis. And what we do is we're looking for some kind of relationship or correlation between the two variables, x and y. So we plot some points and we call these points a scatter plot. We do not connect them. And what we do is we try to describe the association that we see. It is an association or a correlation that we want to see between x and y. Now, because they're plotted on axes, they are numeric in nature, and that's why they're called quantitative. So we have to remember the word DFOX, D-F-O-C-S. And remember, DFOX just is a way of us to remember how to describe the scatter plot. Direction stands for positive or negative, so direct or indirect. So the one that I just drew was positive. F stands for form. That basically means, is it linear in nature or is it non-linear? So is it looking like a line to you or is it looking like a curve? If it doesn't look like a line, say it's non-linear. If it's curved, don't speculate on if it's quadratic, logarithmic, exponential, just say non-linear. If there are any outliers, we want to talk about that. They are unusual points that are removed from the overall pattern. And then there are some points that are specific types of outliers called influential observations. These are outliers that are usually in one direction, like the y direction, and they are ones that if you remove them, they would alter the placement of the least square regression line. So points that are outliers removed from the rest, that removing them will alter the placement of the least square regression line, and also will probably affect the correlation coefficient. The context is just the real world setting that we're talking about, so you want to use the specific language to the question with the variable. So you don't want to just say there's a positive relationship, there's a strong relationship. You want to say there's a positive, strong linear relationship between time and foot size or something like that. And the last one is strength. How strong is the relationship? Is it strong? Is it weak? Is it moderate? That is going to be measured by our correlation. Basically, do the points form a line or not? And how much do they form a line? So we're going to write measured by correlation. Okay. So the correlation coefficient is the letter R. Letter R, correlation coefficient. That is what measures the strength. Specifically, it measures the strength of the linear relationship between x and y. Only linear relationship. Measure strength of the linear relationship between x and y. All right, so the scale that we use for this is -1 to +1. If the absolute value of R is close to 1, we call it strong. If the absolute value of R is close to 0, we call it weak. And the scale we kind of use is from 0 to 0.5-ish for the absolute value, we call weak. From 0.5 to 0.8, we call moderately strong. And then from 0.8 to 1, absolute value, we call strong. So just note that it could be one of the above. R squared is called the coefficient of determination. The coefficient of determination measures the percent of variation or variability on Y that can be explained by x. And the way that you get that is you can either just look at the statistic output, r squared is usually there for you, or you could take r and manually square it and you will get r squared. Now, we're going to talk about the least square regression line. LSRL stands for least squares regression line. The point of the least square regression line is to place it in a way that it minimizes the vertical distance of all the points from the line. And the general equation of the least square regression line is on the reference sheet. But I will tell you it is y hat, which is predicted value of y, equals a plus bx, where the coefficients a and b represent the y-intercept is the a, which is the constant. That's like the initial value in the real world setting. Predicted initial value, by the way, we got to use the word predicted or expected or average. And then the b is the slope. And that's also known as the rate of change. All right. So this is a crash course in regression. And what I want to say about this is the y hat equation, which is the least square regression line equation, it serves as a mathematical model for the data. So what actually happened are the points, but what was predicted or expected to happen was the line. And so that line is like a model for the ideal scenario. So just like we can perform inference for the sample x bar and use it to estimate the population mu, just like we can use inference to estimate p, take p hat and estimate p, we can also use the sample line, which is the y hat line, to estimate the true population line. And that population line is called mu sub y. So notice this says the population least square regression line is shown here in blue. That is in this picture that you guys see here. So we are going to use our sample line to estimate the true population line. So if the sample line down below is the sample equation y hat equals a plus bx, the population line is going to be mu sub y, which is instead of y hat, the mean of all the y's equals, I'm going to use alpha for a plus, and then I'm going to use the Greek letter beta for b, x. Okay, so I'm going to change these symbols here to alpha for a and beta for b. Okay, now what does it mean? The mu sub y is the actual population least square regression line, which is the actual y values of the population. So we use our y hat to estimate all the y values in the population. The alpha is representing the y-intercept of the population line. And the beta, is representing the slope of the population line. Okay, so basically the numbers that came from the sample line are called statistics because they come from a sample and you use them to estimate parameters, okay? So just like x bar estimates mu for means and p hat estimates p for proportions, a, which is the sample line y-intercept, estimates alpha, which is the population line y-intercept, and b, which is the sample slope, estimates beta, which is the population slope. So this is like sample statistics, population parameters. It's the same concept over and over and over again this year. Okay, so little a is a statistic, estimates alpha, and little b is a statistic for the slope, estimates beta. So this is y-intercept, and this is slope. And then the y hat, which is the sample y hat, estimates the true regression line. Okay, so again, it's just all about inference. So now what I'm going to do is talk to you about how I could create a confidence interval using this information. And specifically, they like to create a confidence interval usually for the slope. So the slope, you guys remember, is the b. Okay, that's the b, that's the slope. I'm going to highlight it again for you. So remember the formula for any confidence interval on the reference sheet is statistic plus or minus critical value times standard error of the statistic, right? So remember, for x bar, it would be x bar plus or minus t star times sigma x bar, or standard error of x bar, right? And then for p hat, it was p hat plus or minus z star for my critical value times standard error of p hat, right? So think about, what do you think it's going to be for slope? Well, the statistic, which is going to be this slot here, instead of x bar or p hat, it's going to be the sample slope, which is lowercase b. So it's just going to go right in that same slot here. So the statistic is going to be lowercase b plus or minus. And for this question, we're going to go back to t star for our standard critical value. Sorry, it's the t interval. And then here is going to go standard error of the slope, which is called standard error of b. So notice here, if you guys look at the pattern, I'm going to highlight it. It's going to be standard error of the mean, standard error of the p hat, standard error of the slope. It's the same exact pattern over and over again. And for this situation, because there are two variables, x and y, instead of doing n minus 1, we're going to do n minus 2, because there are two quantitative variables for scatter plots, x and y, right? So that's why we're going to do n minus 2 instead of n minus 1. All right, so now let's actually do an example. I want you guys to skip down to this AP question, because this is really where it's at. They love these questions, and there will be one on your AP. It will be a multiple choice, I promise you this. So it says data were collected on the longitudinal study designed to investigate the relationship between blood sugar levels and brain shrinkage. I'm guessing these are two quantitative variables. It says we're going to do a sample of 22, so that's n. So right away, I want you guys to write degrees of freedom is n minus 2 here, because this is two quantitative variables, x and y. The x variable is always the one here next to the slope, and that is blood sugar. The y variable is the other one, which happens to be the brain shrinkage. Okay, so we're going to do 22 minus 2 here, and we're going to get 20. 22 minus 2 equals 20 for our degrees of freedom. It says, which of the following represents a 98% confidence level, so that's 98, confidence interval for the slope of the least square regression line. Okay, so the first step is you need to find which one is the slope. So if you look here, underneath where it says coef, the slope is the one that's not the constant, because the constant is the y-intercept. So I just want to make a note to self, write down constant equals a equals y-intercept. And basically, if you know that that's the y-intercept, that's not going to be the answer, okay? So anything involving the 15.668 is out. So look, 15.668 out, because that's the y-intercept. We want to do a confidence interval for the slope. So if you know that, then you really just don't care about that y-intercept at all. All you care about is this number, 0.161, okay? So the formula is statistic plus or minus critical value times standard error of the statistic. So the statistic in this case is the sample slope, which is right here, 0.161, plus or minus t star times standard error of that slope. Okay, so the 0.161 is the slope, and right next to it, oh, look how convenient, is the standard error of the slope. Boom, 0.073. So you actually don't have to do any math with that. You just put that in right here. 0.073 is the standard error of the slope, okay? So now let's fill in the last piece, and that's going to be the t star. Before we do, I'm guessing you're already seeing that you got the 0.073 here for all of them, so that actually didn't help us with any process of elimination. So to get t star, we need to look up the degrees of freedom 20, and we need to look up the 98% confidence level. Remember, you're going to go to table B for this, which is the t star table, so do that now. I'm hoping that you guys looked up 98 and 20 and you got this answer, 2.528. So now we're going to plug that into the formula, 2.528 for T star. So if you pick your choice, that would mean that the answer is choice C, 2.528 there. There it is. It's not so bad, is it? See? Pretty good, right? Now look at the next one. The next one says there's a 90% confidence interval for the slope. So again, it's the slope. Write down 0.90 here. and it says they got from negative to positive. There it is. Which of the following statements must be true? So in this case, whenever they give me endpoints, what I want you to do is find the midpoint. To find the midpoint, that is called the point estimate. You're going to add up the two endpoints, and then you're going to divide by 2 to get the midpoint. So do that now. So as you can see, I got a midpoint of 0.674, and that's actually going to be the statistic from the sample, or the point estimate, which is going to be the sample slope, which is B. Okay, so if you look at the choices, it says the slope of the sample line is 1.4348, that's out, and same with this one, this is out, okay? Now, if the sample has a positive slope, that means that it has a positive relationship going up. That means that the correlation coefficient has to be positive because it's a positive slope, and the slope has the same sign as the correlation coefficient, which is R. So we're done. Now, next up, we could also conduct a significance test for slope. And this is the same concept as doing a significance test for mean or significance test for proportions. So remember when we were doing means, the formula would be a t-test statistic, and we would do statistic minus parameter over standard error of the statistic. So if the statistic was x bar, we would do x bar minus mu over sigma, or x bar minus mu x bar over sigma x bar. So similarly, for p hats, we would do p hat minus mu p hat, which equal p over the standard deviation or standard error of p hat. Standard deviation or standard error of whatever it is we're doing. So similarly here, we're going to do the same thing, but it's going to be for the slope. The formula for a t-test statistic is statistic minus parameter over standard deviation or standard error of the statistic. So the statistic for slope, remember, is B, and that's used to estimate beta. This is the statistic, and this is the parameter. So the statistic here is going to be B minus the parameter is going to be beta over the standard error of the slope, the standard error of B. And remember, we got that standard error from that last question there, where we just looked here under SE for standard error, and we just looked next to the slope, and there it was, okay? So the hypothesis for slope. Now, if the slope, if there is no linear relationship between x and y, then the slope would actually be 0, which would mean that as x increases, y does nothing. Y just doesn't do anything. Okay? That actually means no relationship. So that is a horizontal line, and a horizontal line has a slope of 0. So HL would be beta, because it's the parameter, equals 0. And in words, that means there is no linear relationship between x and y. Okay, and that kind of makes sense because HO always means no. And then the HA, it would depend on if you thought it was a positive, negative, or no relation, not equal to relationship, one-sided or two. So let's say we predicted that there was a positive relationship and a positive slope. I would do beta is greater than 0. There is a positive relationship between x and y. I would do less than if I thought there was a negative relationship between x and y. And I would do not equal to 0 if I'm just saying there is some kind of linear relationship between x and y. So it says here to obtain the p-value, and I'm going to highlight this, we have to look at the line with the slope, and we have to look next to it, and there's going to be a p-value. The p-value in the statistic output is usually a two-sided p-value. So if we want a one-sided p-value, we have to divide the p-value in half. In this last question here, there is no p-value next to it, but in the previous one, which I skipped over, I'm going to show you, there is a p-value here. This is the slope, the miles driven. This is the coefficient for the slope, lowercase b. This is the standard error of the slope. And then right here is the p-value, okay, which happened to be 0 in that question. So here is an example. They're talking about infants crying more easily, who may be more stimulated than other infants. And they have the cry count for the infant, and they have the predicted IQ for the infant here. And it says find the t-score for the slope. The t-score is the t-test statistic, okay? So remember, the formula is statistic minus parameter over standard error or standard deviation of the statistic. Okay, so in this case, so the statistic is the b, the slope of the sample, the parameter is the beta, and the standard error is SE of B, okay? So the statistic here is the B. So that's this. The cry count, remember it's always changing from question to question, but this is the slope. Remember this constant is the y-intercept. It's always going to say constant for the y-intercept. We don't care about that one for this. So right now you're just going to plug in 1.4929 for the statistic. The parameter is beta, and in our null hypothesis, it's always assumed to be 0, meaning there's no relationship or no slope between x and y, no slope. So you put 0. You don't have to write 0. And then the standard error is right here. Boom. You just put that in the denominator, 0.4870. So if we divided those two numbers, let's see what we get. In the home screen, if we do 1.4929 divided by 0.4870, and we end up getting a t-score of 3.07. You may be like, oh, okay, 3.07. Well, it turns out that that number is actually right here on the statistic output. It's right next to the underneath the column that says t-score, 3.07. There it is. That's the test statistic, okay? Test statistic. And now the p-value would be right here, 0.004. So if p-value is 0.004, but I reject the null. And because p is low, it's less than 0.05, I reject HO. If you reject HO, that means that you can conclude in favor of the alternative hypothesis. So if the alternative hypothesis was a two-sided tail, which is what we were just talking about, it would be a not equal to sign. Then the p-value would be 0.004. If it was a one-sided tail, then I would have to take the 0.004 and divide it by 2, and then that would be 0.002. So lastly, if you skip to some of these AP questions, skip past 1, skip past 2, go to number 3. This is kind of a straightforward question here. This is an AP question related to a t-score for slope. So it says they did a research study and they had a negative linear relationship between the variables of number of hours per week spent exercising, which is the exercise time, that's the x variable, and the number of seconds it takes to run one lap around the track. So the more you exercise per week, the less time it should take you to go run a lap around the track, a quarter of a mile. Assuming that the conditions for inference are met, which of the following is an appropriate test statistic? So that's the t-score for the null hypothesis that the slope is 0. So they're saying if HO beta equals 0, we want to find the t-score for the slope. So again, this is the y-intercept, the constant, and that's letter A, and the slope is the B. So you can cross out the y-intercept and focus on the slope. And again, the test statistic formula is statistic minus parameter over standard error. So the statistic is negative 2.20, because that's the B. The parameter is beta, which you're presuming is 0. And the standard error of the slope, it's right next to it in the statistic output. It's 0.07, because you're looking right under there. So really that's it. You just have to look for that in the answer choice. And it's negative 2.20 divided by 0.07. That's it. It's not so bad, right, people? Thank you.